Thank you. So good morning, everyone. So our speaker today is Ortrud Oellermann. So Ortrud is from University of Winnipeg in Canada. And Ortrud will be speaking today on the threshold dimension and the strong threshold dimension of graphs. Ortrud.
Thank you, Nadia. Thank you, everybody, for chiming in. Yeah, so the work on the threshold dimension was joint work with Lucas Marlin and undergraduate Matthew Murphy. And the work on the threshold strong dimension was joint work with a number of women. I've listed all their names here. And this workshop, work was started at a workshop in Minneapolis last year. Okay. So I'll give you first some background on the metric dimension and the strong dimension before I get into the threshold dimension and threshold strong dimension. So first of all, just a motivation for the concept of the metric dimension. Suppose we are given a distance detecting device for a network. The question is, can we uniquely determine the location of an intruder in the network? Okay, so let's take, for example, this very simple network here. This is a path network. Suppose I place a detecting device at this white vertex here. Then I've labeled the vertices with their distances to that white vertex. So if I place that detecting device there and I get the message there is an intruder distance 3 away, then for sure I know that that intruder must be at that location where it's labeled 3. However, if I get the message that it's distance 1 away, well, it might either be here or here, right? So we can't uniquely determine the location of the intruder in that case. Now, suppose I move my detecting device to the end of that path, okay, then you'll see that all the vertices have different distances to the device. And so in this case, when we place it there, we can uniquely determine the location of an intruder. Okay, so you can easily see that this can be extended to paths of all possible orders. So the metric dimension for paths is just going to be 1. How about cycles? Now, by the symmetry, it doesn't matter where we place it. So let's place it at the top there. Again, I've labeled the vertices with their distances to that white vertex. And you can see that the location of an intruder wouldn't be uniquely determined if the message that we receive is that it's 2 or 1. Okay, so one device is not going to be enough in this case. So let's now place another device next to that one. And what I've done now is I've labeled the vertices with ordered pairs, where the first coordinate indicates the distance to the first vertex. I'll call it W1 here. And the second coordinate indicates the distance to the second vertex. Let's call that W2. Okay. So now, for example, if the first detecting device gets the message there's an intruder distance 2 away, and the second device gets the message that there's an intruder distance 3 away, we know that it must be at this particular point. So the vectors that are associated with each vertex, they're all different, right? They're distinct. So 2 devices is enough. All right, so let's make this more formal. For my talk, I'll be assuming that all graphs are connected. So we say vertex W in a graph resolves to vertices U and V if the distance from U to W is different to the distance from V to W. Okay. And a set of vertices resolves the entire graph if every pair of vertices is resolved by some vertex of W. And the smallest resolving set will be referred to as a metric basis or sometimes just a basis, and its cardinality is called the metric dimension, which we denote by beta of G. So as we did for cycles, if we have a set W, W1 through WK, we can associate with each vertex V of the graph a K tuple, a K vector, where the ith coordinate is the distance from the vertex V to WI. And we call these the distance vectors relative to W. So W is resolving if and only if the distance vectors are all distinct. So what's known about the metric dimension? Well, it's known that paths are the only graphs with dimension 1. Complete graphs, these are graphs where every two vertices are joined by an edge, are precisely the ones of order n with dimension n minus 1. And for all other graphs, the metric dimension lies strictly between 1 and n minus 1. Okay, it's a difficult problem. It was first mentioned by Gary and Johnson in 1979 that it's an NP-hard problem. The first proof I saw, published proof I saw, was due to Kuller and his co-authors in 96. Algorithms exist for some classes of graphs, probably the most well-known being the algorithm for trees, which I'll talk about, and then the other classes as well, as for example, outer planar graphs and graph products, co-graphs. But on the whole, it's largely still open. A nice study was done for this invariant on random graphs. So,
pardon me, could I make an interruption for a moment?
yes.
You say algorithms are known, but there's always an algorithm.
Well, yeah, okay. I mean an efficient algorithm.
By efficient, do you mean polynomial time?
Yes, yes, polynomial time. Yeah.
Okay, was some argument. Okay, thank you. That's what I wanted to know.
Yeah. So I want to describe the algorithm for trees to you. So a major vertex in a tree is one of degree at least 3. We say a leaf U is a terminal vertex of a major vertex if the VU path has no major vertices other than V itself. And if U is a terminal vertex of a major vertex V, then the VU path is called a limit V. Now, the number of terminal vertices at a major vertex is called the terminal degree. So we'll denote that by TER of V. So Slater, back in 1975, he was the one that introduced the concept of the metric dimension. And at about the same time, Harari and Malta independently studied the same parameter. They both showed that if T is a tree, that's not a path, and S is the set of major vertices with positive terminal degree, then the metric dimension is the sum of the terminal degrees of the vertices minus 1 over all vertices in my set S. And a metric basis can be obtained by selecting for every vertex with terminal degree greater than 1, a vertex from each but one of its limbs. So for example, in this tree that I've shown you here, the major vertices are those that I'm putting a red dot next to, okay? And the terminal degree, for example, of this one here is 3. So the theorem tells us that we can get a metric basis by selecting vertices from 2 of its limbs. And this you do for each of the major vertices of terminal degree at least 2. Okay, so that using that for all the major vertices, we see that this tree has dimension 6. Then a number of years later, Sheba and Tanya asked whether every 2 graphs of the same order and with the same distance vectors relative to some resolving set are necessarily isomorphic. Well, it turns out that this needn't be the case. Here I've shown you 2 very simple graphs of order 6. And next to each vertex, I've given the distance vector relative to the resolving set consisting of the white vertices in each graph. Okay, and you notice that they're the same for both graphs, but they're not isomorphic since these 2 vertices are not adjacent in the first graph, 2, 3, 3, 2, but they are adjacent in the second graph. So in order to resolve their question, they introduced the concept of a strong resolving set. So a vertex W in a graph is said to strongly resolve to vertices U and V if either a shortest UW path contains V or a shortest VW path contains U. So just a sec here. All right, so we have we have either a shortest UW path contains V sits somewhere, or you switch them around. These could be switched around. So you can see certainly V would be closer to W than U is if this happens. So certainly if they're strongly resolved by W, they will be resolved. A set of vertices, again, is going to be a strong resolving set for the graph if every pair of vertices then is resolved by something in W. Okay, strongly resolved. And a smaller strong resolving set, I'll call a strong basis, and its cardinality, the strong dimension, which we'll denote by beta sub S of G. All right, what's known about these? Again, paths are the only graphs with strong dimension 1. Complete graphs are the ones of order n and strong dimension n minus 1. Okay. The problem of finding the strong dimension of the graph is NP hard. And again, some polynomial algorithms exist for certain graph classes. Shebo and Tanya, in their seminal paper, observed that if T is a tree, then the strong dimension is just one less than the number of leaves. So if we take a look at the tree that I'd shown you earlier on, for which we computed the metric dimension, this one has 12 leaves. So we need to pick all but one of those leaves to get a strong basis. So the strong dimension here is 11. Okay. All right, there's a really useful tool for finding the strong dimension of a graph. And it turns out the tool that we're going to use is a transformation to the vertex covering problem. Okay, so let me tell you how we do that. We say that if U and V are vertices of a connected graph, then V is maximally distant from U. We denote this by V MDU. If every neighbor of V is no further from U than V. In other words, for every x in the neighborhood of V, the distance from U to x is less than or equal to the distance from U to V. Now, if we have symmetry here for a given pair, so U is maximally distant to V and V is maximally distant to U, then we say they are mutually maximally distant. Okay, and I'll denote that by U is MMD from V. And so now we are ready to describe the transformation. We construct a graph called the strong resolving graph, which I'll denote by G subscript SR of G, which has the same vertex set as G, and two vertices of this graph are adjacent if and only if they MMD from one another. And then it turns out that the vertex covering number of the strong resolving graph equals the strong dimension of the graph. And a minimum vertex cover is a strong basis. So let's take a look at this graph here. This is, I guess, a 5-pan. All right, I'm going to label this leaf here. I'm just going to call that V, and let's call these vertices X, Y, and Z. And I'm just going to explain why some edges are in there and some are not. All right, so let's take V. It is certainly maximally distant from every vertex in the graph because it doesn't have a neighbor that can be further away from any other vertex. So it's maximally distant. But of course, not every vertex is maximally distant from that leaf. For example, X is distance 2. This vertex X here is distance 2 from V, but it has a neighbor Z, which is distance 3 away. So X and V are not MMD. So that's why we don't have an edge between V and X in the strong resolving graph. However, if I look at the pair VZ, well, they are MMD from one another because Z now is maximally distant from V because its two neighbors, X and Y, are no further than Z away from V. Okay, X in fact is distance 2, so it's closer, and Y is the same distance. So that explains why we have this edge between V and Z in the strong resolving graph. Okay, and it takes 3 vertices to cover the edges in the strong resolving graph. So that tells us that the strong dimension there of that graph is going to be 3. All right, so I'm getting closer now to the topic for today's, main topic for today's talk. Unlike some graph parameters, such as, for example, the connectivity, which cannot decrease when we add edges, the metric dimension actually can decrease when we add edges. So take, for example, the star. Okay, the star, by our tree theorem, has metric dimension 3. But if we add an edge between 2 of the leaves, then it actually drops to 2. So it gets less. Now, from our detecting device point of view, or from an applied perspective, reducing the number of distance detecting devices in a network by adding links represents a cost savings, right? Adding the links is very inexpensive compared to purchasing a detecting device. Now, the metric dimension actually can also increase when we add edges. For example, I showed you those cycle graphs. They have metric dimension 2. They can be obtained from the path by adding an edge between the 2 leaves of the path, right? And the path has dimension 1. So in that case, it goes up. So that prompts the question, by how much can the dimension decrease if we add edges? And by how much can the dimension increase if we add edges? Okay. Well, for the first question, this always depends, of course, on the graph, right? In the second case, it's always going to be n-1, because you can add all the edges from the complement and construct the complete graph, and then you have a graph with dimension n-1, which is as big as it goes, right? So hopefully, from both an applied and theoretical perspective, you can see why the question of decreasing the dimension of a graph by adding edges is the more interesting one. So this minimum, the smallest dimension that we can get by adding edges to a graph, is called the threshold dimension. And we'll denote this by tau of g. Okay, so that's the notation we use. And I use U of g to denote the supergraphs. By supergraph, I mean in this case, precisely the graphs obtained from G by adding edges. If H is a supergraph that realizes this minimum, then we say H is a beta threshold graph. Okay, so let me sing along. All right, so graphs whose metric dimension cannot be lowered by adding edges will be called beta irreducible. In other words, G is beta irreducible if and only if the dimension is equal to the threshold dimension. Otherwise, we say it's beta reducible. Right, the exact same concepts exist for the strong dimension. So the threshold strong dimension, which I'll denote by tau sub S of G, is the minimum strong dimension among all supergraphs of G. And we have the same idea of a beta S threshold graph. In other words, a graph, a supergraph that realizes this minimum is called a beta S threshold graph for G. And graphs whose strong dimension cannot be lowered by adding edges will be called beta S irreducible. Okay. Otherwise, if they're not beta S irreducible, we say they're beta S reducible. All right, just some simple observations about these two parameters. Paths are the only graphs with threshold dimension and threshold strong dimension equal to 1, and they turn out to both be beta and beta S irreducible. Graphs with dimension and strong dimension 2 are also beta irreducible or beta S irreducible. And the reason is because if they have strong dimension 2 or dimension 2 or strong dimension 2, they're not paths, right? And they're connected. And by adding edges, you can never produce a path, right? So these graphs are also irreducible. Okay. K14 is beta and beta S reducible, but every beta threshold graph, not every beta S beta threshold graph is a beta S threshold graph. For example, the first one that we saw earlier on is a beta threshold graph for K14, but it's not a beta S threshold graph. If we were to construct the strong resolving graph for that graph, we would see that it's a K4, which has vertex covering number 3. So it hasn't reduced it, but if we add 2 edges, then we get a beta S threshold graph for K14, okay, which in this case is also a beta threshold graph. So there can be lots of different graphs that are threshold graphs for a given graph. All right, so we saw early on that this tree has dimension 6 and strong dimension 11. So my question to you is, what do you think the threshold dimension for this tree is? And what about the threshold strong dimension? How might we determine that? Well, from the definition, we know we have to add edges and then try and bring it down as much as we can, right? But if we use some kind of brute force approach, in particular, if we look at all possible subsets of the edges from the complement, there are a large number, right? This number of possible sets of edges we can add to this tree. And in each case, we'd have to find the dimension to see if we get an improvement. We have to take the smallest of these, right? So using this brute force approach isn't really very viable, okay? So hopefully I'll be able to convince you that these embedding results I'm going to talk about next are really quite nice for us to be able to find the threshold dimension and threshold strong dimension of graphs. All right, by an embedding of a graph G and a graph H, we mean an injective map, phi, from the vertex set of G to the vertex set of H that preserves adjacencies. So if UV is an edge of G, then phi of U, phi of V is an edge of H. In other words, phi is an injective homomorphism. Now, if we have an embedding phi of G and H, we let phi of G denote the subgraph of H induced by the set, the image set of the vertices of G. Okay, so it's possible that we may have to add some edges. I'll show you an example. Now, it turns out that both the threshold dimension and the threshold strong dimension can be described in terms of the smallest number of paths whose strong product admits certain types of embeddings of these graphs. Now, the strong product of 2 paths is a 2-dimensional grid with diagonal edges. So I'm not going to give the formal definition, but here you take 2 paths, here I've labeled the vertices 0, 1 through 4 in this case, and then a vertical path, and you form the strong product, okay, in this manner. And with this labeling of vertices, so that's important, I want you to note that the every vertex can be described in the natural way with an ordered pair. So this one, for example, would receive the coordinates 4, 3, right? That ordered pair describes that particular node right here. Okay, so, and then the strong product of B paths is really just the B-dimensional version of this grid. So let's take an embedding here, show an embedding of this graph here that we looked at earlier on. In the strong product of 2 paths on 4 vertices. Okay, so here in the middle, we've shown an embedding. So you can see the graph sitting there, the black edges. And I said the image graph is the one induced by these. So these 2 vertices here are image vertices that are adjacent in the strong product, but they weren't as adjacent because of edges that existed in G, right? So we have to add that edge there. All right, so now this is the nice embedding that we are after for the threshold dimension. So let G be a graph and W a subset of the vertex set and P a path. So when we talk about a path, I always mean a path that is big enough. We can always make it long enough that we can do embed a graph in there. So the important thing for us is going to be the smallest number of paths that we can embed, and we'll assume that we can make the paths big enough for our purposes. So a W resolved embedding of G in the strong product of K paths is an embedding of the graph so that for every X in the vertex set of G, the vertex phi of X, in other words, if we look at the image of the vertex X and we look at its coordinates in that grid, remember how I showed you how we can assign coordinates to the vertices in the strong product? So we look at the coordinates of the image, is actually the distance vector relative to the image of the set W. In other words, the ith coordinate of phi of X is exactly the distance between phi of X and phi of Wi in the subgraph induced by the image, phi of G. That's a W resolved embedding. All right, we showed that if the dimension of a graph is B and W1 through WB is a resolving set of the graph, then G has a W resolved embedding in the strong product of B paths. So that's nice. If we have the dimension, then we can find such a nice embedding. Okay, and it's a very simple idea. We just map X to the distance vector for X relative to the set W. Okay. Right, later on, with the second group, we also showed that the distance in the image graph between phi of X and phi of Wi is equal to the distances in the strong product between phi of X and phi of Wi. So normally we know that this is going to be greater than or equal to that distance, right? Because a subgraph maybe doesn't preserve the distances between all pairs of vertices, but in this case, it preserves the distances to the images of the resolving set. Okay. Right. So we have equality here. That's basically what we showed there. So going back to that example earlier on, how did I get that embedding? Well, it turns out that the dimension of this particular graph is 2, and W1, W2 is a resolving set. So if I label the vertices with their distance vectors, then those become the coordinates of the images. So this vertex here with whose distance vector is 1, 1 gets mapped to the vertex 1, 1 in the strong product and so on. All right. So this then is a W1, W2 resolved embedding of the graph in the strong product of P4 with itself. All right, we proved that the threshold dimension of G is the smallest cardinality of a set W of vertices for which there is a W resolved embedding of the graph in the strong product of cardinality of W paths, each of sufficiently large order. So remember that tree that I showed you early on, and I asked you what you think the threshold dimension and threshold strong dimension of this tree is? Now for this tree, I've shown here in the middle an embedding, okay? And in fact, it's a W1, W2 resolved embedding of this tree in the strong product of two P6s. Okay. And this is the subgraph induced. So we have to add a bunch of edges between vertices to get the subgraph that is induced by the image. Now, take, for example, this vertex here. It has coordinates 4, 5, right? So our result says, therefore, this vertex should be distance 4 from the image of the first W vertex. So, and that's the case. Here's a path of length 4, it's the shortest path, right? And there's a path of length 5 to the second one. Okay, so that's the distance. So in fact, one can check that the distances from every single vertex to these two image vertices, W1 and W2, is preserved. And notice here that W1, W2 is not a resolving set for the tree, right? Remember, it has metric dimension 6, so it's not a resolving set. So here's a W1, W2 resolved embedding of the tree, where now W1, W2 is going to be the resolving set of this graph phi of t. And that's the supergraph that we are after, right? The one with the smallest dimension that has t as a spanning subgraph. All right, so that was the threshold dimension. How about the threshold strong dimension? Well, at first we asked ourselves, is it even different? Perhaps the threshold dimension and threshold strong dimension of a graph are actually the same thing. We didn't think it was, but we had trouble finding examples. So here is an example of a graph with threshold dimension 2 and threshold strong dimension 3. Okay, so the embedding actually shows it's a W1, W2 resolved embedding in the strong product of two paths. It shows that the threshold dimension is 2. Okay. And in fact, we believe that the difference now can be made as big as we want it to be between the threshold strong dimension and the threshold dimension. If we take that graph that we had on the previous slide, I'm going to draw that, circle it here. Then we can take several copies and glue them together along these two vertices and then add a couple edges. Okay, and we can keep repeating this. And as we increase the number of times we do this, we believe that the threshold strong dimension does go up. It's at least been verified for small graphs. All right, so I want to just make some observations here that will lead to the additional condition that we need to get a geometric characterization for the threshold strong dimension. So suppose the threshold strong dimension is B for a given graph G. Then we know that there is some supergraph H, a threshold graph, for which the strong dimension is equal to E. So if W is a strong resolving set for H, it's got to be a resolving set for H as well, right? So if W is a strong basis for H, there is a W resolved embedding phi of H, and therefore of G in the strong product of B paths. Yeah, that follows from the first lemma that I stated for you. Okay. Now remember, W is a strong resolving set. So for every two vertices, X and Y, there exists a vertex W in the set W, such that either a shortest phi X phi W path contains phi Y, or a shortest phi Y phi W path contains phi X. So say the first one. Okay. Now, since phi of H preserves distances to the vertices of phi of W, that was the second lemma I stated, we can see that a shortest phi X phi W path contains a shortest phi X phi Y path, and using triangle inequality, one can then show using the triangle inequality, one can show that. So here is the geometric characterization then. Let G be a connected graph and W a set of vertices of G. Then W is a strong resolving set for some supergraph H of G, if and only if for some path P there is a W resolved embedding phi of G in the strong product of K parts such that phi of G is an isometric subgraph. So it doesn't only preserve the distances to the vertices of phi of W, but it also preserves the distances between all other pairs of vertices. So isometric just means the distances between every two vertices in the subgraph are the same as in the graph. In this case, that means the strong product. So the threshold strong dimension then is the smallest cardinality of a set W for which there is a path P and a W resolved embedding phi of G in the strong product of cardinality of W parts. That's an isometric subgraph in the strong product. So going back to the embedding that I've already shown you, it turns out that this is actually an isometric embedding in P6 cross P6. For example, if I pick this vertex here and this one, okay, so neither of those is the image of W1 or W2. The distance in this in the in the graph is 3, and the strong product is 3, right? For example, here's the shortest path, but there's another one that goes through the black graph here. Okay, so the distances between any two vertices in that image graph is the same as in the strong product. So that then tells us that the threshold strong dimension of that tree is also 2. Okay, so instead of having to go through all those different sets of edges and adding those one at a time and then calculating the metric dimension in each case, we can see it from this embedding that it's true. And then therefore this black graph here would be a threshold graph in both cases. All right, what else is known about trees? Well, not that much. We know that if T is a tree with metric dimension 2, then its threshold dimension is going to be 2. We're able to show that whenever we pick a tree and the metric dimension is bigger than or equal to 3, then we can find a single edge whose addition to T brings the dimension down. So we can always bring the dimension down by the addition of some edge. And so an immediate consequence of that is that the threshold dimension of a tree with dimension 3 is 2. Okay. And it turns out if we have a tree with metric dimension 4, then we can find 2 edges in the complement, which when added to T brings the dimension down to 2. Okay, so just 2 edges have to be added. Okay. So in summary then, if the metric dimension is 2, 3, or 4, then the threshold dimension is 2. Now we can't extend this to trees with dimension 5. For example, the star K16 has dimension 5, but it does not have threshold dimension 2. So we can't extend that any further. Now for the threshold strong dimension, we were able to obtain the same type of result. In other words, those with strong dimension 2, 3, or 4 have threshold strong dimension 2. However, the result is proven completely different. And first of all, the class of trees for which we have this happening is certainly different than the classes of trees where we have dimension 2, 3, or 4, right? But we have to add far more edges to get the threshold, strong threshold graphs for trees of small dimensions. So I've just illustrated here one such embedding that we would have used in the proof here on the right-hand side. Okay, so this is a Y3U2 resolved embedding. That is an isometric subgraph of P8, strong product P8. Okay, so that's just an illustration of how the proof would have handled this particular case. So we add lots of edges, not just 2 edges, which was the case for the dimension. All right, one might also ask how big the difference between the dimension and the threshold dimension can be. So maybe as the dimension goes up, the threshold dimension will also go up. What can be said? Well, it turns out that actually the difference can be quite big. So let's take this example here, and this can be generalized. So we take in the middle here a path on n vertices, and we attach 2 leaves to every single vertex on that path. And I'm going to call this, okay, so this of course is a specific case, but in general, for general n, we'll denote that out by L3n. So do you remember what the metric dimension of L3n is? How many leaves do we have? Well, we have 2n leaves in this one, right? And at each major vertex, we have to pick one representative from all but one of its limbs. So we have to pick n. So the metric dimension is n. And the strong dimension is 1 less than the number of leaves. Well, the number of leaves is going to be 2n. So it's going to be 2n minus 1, right? So in the middle, I've shown an embedding of this tree in the strong product of 2 paths. Okay, and this is the subgraph induced by that embedding here. And this is a W1, W2 resolved embedding. Okay, well, this is actually I guess the image. Yeah. And this is an isometric subgraph of the strong product. So it's possible that graphs with very large dimension and very large strong dimension have very, very small, as small as we can get, threshold dimension and threshold strong dimension. All right, so what else is known? Well, for the rest, we just have bounds. For trees, we have bounds, and we've extended those ideas to all graphs. Okay, so I don't want to get bogged down too much on this function. So if x is a positive real, then d sub x is the smallest positive integer such that x is less than or equal to 2 d to the x plus dx. So for example, if x is 4.5, then dx is easily seen to be 2. Okay. So x lies in this interval that I've described here. Okay. And dx is less than or equal to the log of x to base 2, a ceiling of that. All right, so roughly speaking, dx is going to be the log of x to base 2. So if T is a tree of order n, then the threshold dimension of the tree is less than or equal to dn. Right? And this is the idea. Well, if T has at most dn leaves, then already we know that the metric dimension has got to be less than dn. Okay. Well, what if T has more than dn leaves? What we do is we select a set W, okay, with dn vertices in it. Okay, that will serve as our resolving set. The remaining vertices, so this would be v of t minus w, sits up there. Okay, and there are less than or equal to 2 to the dn vertices up there, less than or equal to, possibly equal. Okay, but the point is this: we can assign to every vertex in here a different neighborhood in W. So a different neighborhood because this has 2 to the dn possible subsets. So every 2 vertices are assigned a different neighborhood, and that describes a supergraph. Once we assign the neighborhood, we add those edges, and W becomes a resolving set. Right? So we can bring down the metric dimension by using that trick. Okay, and the bound is best possible, for example, for stars. Right, same result holds for threshold strong dimension. The only difference is slightly different construction needs to be used. And then we extended this idea to k-chromatic graphs. Okay, so for k-chromatic graphs, we can partition the vertex set into k-independent sets. Okay, and we can construct a supergraph that has threshold has dimension at most k times f of n over k. F of x is very similar to d of x. Okay, the only difference is with the endpoints for these intervals, and that's technical details there. But you can think of it as roughly being log of that number, right? So this is roughly log of n over k to base 2. So the threshold dimension is bounded by k times that plus 1 minus 1. Okay. And this bound is sharper. It would be achieved by some complete k-part type graph where all parts are roughly the same. So basically in each part, what we do is we again have a vertex, a set of vertices, and the rest receive different neighborhoods in that set. And then we take the union of these parts and put them together to get a resolving set for the graph. And then of course we have to add in all the edges between the different parts as well. Right, a very similar result holds for strong dimension here. I've stated it more in terms of cardinalities of the color classes, but it's the same idea. Slightly different construction now. All right, I'm just going to talk very briefly about irreducible structures now. We don't know how to recognize them. We have no algorithm for recognizing irreducible structures. We do know they exist for every pair of integers n and b. With n greater than b, there is a beta irreducible graph of order n with metric dimension b. Okay, and the same is true for the strong dimension. So the beta is irreducible graphs of a given order and dimension. All right, so that's as much as I'm going to say in terms of new results. Just wanted to point out that we were inspired also by these embedding results to obtain a solution to an open problem that was posed by these authors here back in 2018. They had asked what graphs can be realized as strong resolving graphs of some graph. And in particular, they asked graphs, for those graphs with vertex covering number 2, which one of these can be the strong resolving graph of some graph? All right, so it turns out, provided the graph doesn't have a K22 as a subgraph, it's going to be can be the strong resolving graph of some graph. And like I said, the embedding results actually inspired the construction that gave the solution to this problem. Now, at this point, you may wonder how much change we can affect by just adding a single edge, right? Okay, and this question had been looked at for trees. So for trees, when we add an edge, the metric dimension can drop no more than 2, okay? And it can increase no more than 1. So that was known. More recently, in a paper on arXiv, these authors studied what they call the robustness of the metric dimension to adding a single edge. They showed actually that lower bound we had for trees is true for all graphs. Okay, you can never bring it down by more than 2. But they showed that there is no upper bound, comparable upper bound for general graphs by showing that there are graphs of some order n having dimension less than log n, for which the addition of a single edge, some edge, brings the dimension up to order of n. Now for the strong dimension, again, we can bring it down by as much as 2, okay. But there is no upper bound as we had here for the dimension. There's no comparable upper bound. And actually, you can just take the paths that we looked at and add a single edge to form a cycle. It turns out that the strong dimension of cycles is quite large. So just a few open problems then. We still don't know if the problem of finding the threshold dimension and threshold strong dimension, whether these are NP hard or not. So those are open problems. Here's a question we weren't able to answer. What's the smallest dimension that a graph on n vertices and m greater than or equal to n minus 1 edges can have? So what's the one with the smallest dimension for a given order and size? All right, here's a question. Is there a tree for which the threshold dimension is not equal to the threshold strong dimension? And if so, how big can the difference between these two be? Okay. So that's not clear whether the answer there is yes or no. And then recognizing irreducible structures. Yeah, is that a difficult problem or not? I suspect it probably is. Right, and that's it. I just wanted to thank everybody for listening, and I acknowledge some support that we got to do the research.
Thank you, Ortrud. That was a very nice talk. Questions, everyone?
I'd like to ask, what is the people seem to be interested in metric dimension? Why? Where does this come from? That's my question.
Yeah, well, did you see the example, the motivational example I used in the beginning?
Either I didn't see it or I forgot.
Okay, so we have these, we have detecting devices, distance detecting devices that help us uniquely determine the location of an intruder in a network.
Do we actually have such devices?
I don't know. That was used as a motivational example by Slater. Now I can give you some other examples. People have also used this to aid the navigation of robots in a graph space. So that you want to be able to uniquely determine whether the location of a robot in a graph network, right? So say it moves along the edges of a network, so you can then determine its location.